Hi, everyone. And here we are for our last lecture of Unit 3 for CHY 113. Um, I don't have any slides associated with this, and so I'm sorry, but I don't have any warm-up questions for today either. It's just going to be a good old-fashioned chalk talk on a subject called hybridization. And so when we talked about quantum numbers and when we looked at sp, d, and f types of orbitals, those are a great way for us to describe sort of the arrangement of electrons around just a single atom. It turns out that we have to tweak that a little bit when it comes to what atoms are actually going to do when they start to engage in bonding. And so that's what hybridization is all about. And so let's go ahead and pull up our chalkboard here. And in order to start to make some sense out of this, we do have to first sort of define a couple of other, or we have to think of some bonding in some other ways and define bonds in new ways. We have what we call sigma and pi bonds. Yeah. Sorry, I was having a little trouble with my Apple Pencil, but it seems to be working now. And so when we think about sigma and pi bonds, if we just think about a sort of a generic compound, or if we think about even something like maybe CH4, so maybe methane. All single bonds are what we call sigma bonds. And so each of these single bonds connecting our hydrogens to our carbon, these are all sigma bonds here. Pi bonds are multiple bonds. And so if we have a compound maybe such as CO2, so if we do the Lewis structure for CO2, oh, too many electrons there. Let's fix that. This is what happens when you try to do Lewis structures in your head without writing it out. There's our Lewis structure, though, for CO2. And so each of these double bonds actually consist of, so here's our double bond here. This double bond consists of one sigma bond and one pi bond. Same as this one here. One sigma bond and one pi bond. And so anytime that we're picturing any sort of multiple bonds, one of those is always a sigma bond. The other, either one or two, if it's a triple bond, are pi bonds. And so if we have maybe HCN, so there's our Lewis structure for HCN. Our triple bond here consists of one sigma bond, and now there are two pi bonds in there. And between the hydrogen and carbon, we have one sigma bond. And so that's just sort of different ways to define bonding. And we're going to see how that comes into play and where sigma bonds and pi bonds come from as far as what types of orbitals are doing things in order to form these bonds. Because remember, that's all bonds are. We have to sort of think back to that basics. Bonds, each bond is two electrons. And so when we were looking at quantum numbers, we talked about electrons residing in the different types of orbitals, sp and d, and so forth. And so what we're going to do now is just get into a little bit of detail of what happens with those orbitals when this bonding occurs. What happens to these orbitals when a sigma bond forms or when a pi bond forms. And so if we look at something like a carbon atom, so just a regular old carbon atom, the electron configuration of 1s2, 2s2, 2p2. Remember that it's our valence electrons only, which are actually involved in bonding. So our 2s2 and our 2p2 electrons are the ones involved in bonding here. And so let's look at a bit of an orbital filling diagram for just these valence electrons for carbon. So here's our 2s, and we have 1, 2 electrons there. Here's our 2p orbitals. Remember, Hund's rule tells us those are going to fill singly, 1, 2 orbitals, or 1, 2 electrons. And so there's our orbital filling diagram for a carbon atom. Now, if we think about carbon bonds, though, and so if we think about something like methane, which I had up earlier. So carbon's going to form 4 equal bonds, each to different hydrogens. But if we look at the arrangement of electrons here, and if we remember that each bond consists of 2 electrons, we start to see that this arrangement doesn't really work out. If we look to where electrons might be able to pair up, then okay, we can pair up in an orbital here, we can pair up in an orbital here. This one's empty, we already have 2 electrons here. And so something's going on here. Something must be different about the orbitals when carbon actually forms into these 4 bonds. And indeed, what does happen is that once carbon starts to get into a situation where it's going to bond, these s and p orbitals, our 1s orbital and our 3p orbitals, speaking about the actual number, not quantum number 1. And so our s orbital here from 2s, so this s orbital here and these 3p orbitals, what these are going to do is actually mix together and hybridize. And so these are going to, like I said, mix together. That's better. And instead of having an s orbital and 3p orbitals, we are instead going to mix these together and form 4 equal, what we call sp3 orbitals. That just comes from the fact that in order to make these 4 different orbitals, we took a single s orbital and we took 1, 2, 3 p orbitals, sp3. And that got us to 1, 2, 3, 4 different orbitals now. And we have these 4 electrons that can now occupy these singly. Now we see pretty clearly 4 different unpaired electrons in these 4 sp3 orbitals that can now come in and allow hydrogen, the single electrons coming from each hydrogen, to now pair up in order to form our 4 sigma bonds. And so that's what hybridization is. Hybridization is when for now, we're just talking about S and P, when the S and P orbitals mix together to form these hybrid orbitals, which then are able to participate in bonding. And these hybrid orbitals have slightly different shapes. And so the shape of a hybrid orbital, so remember an s orbital, the shape is just this sphere. P orbitals have the sort of dumbbell shape. An sp3 orbital is sort of shaped like this. And then what can happen is, so if this is our carbon here, there's one of the sp3s, and then hydrogen comes in with its just s orbital and forms that overlap. So this sort of overlap here would be those 2 electrons forming the bond. And so that's all hybridization is it's this mixing of the orbitals in order to make sigma bonds. Now, what's going to happen is that an atom will hybridize in such a way that it will make a number of hybrid orbitals equal to the number of sigma bonds that must form. And so let's take a look at another example here. Let's take a look at a molecule of ethene. Ethene consists of a double bond, two carbons double bonded to each other, and then hydrogens hanging off each of the carbons. And so let's focus on this carbon right here. And so that carbon has to make, so it's got these two just single bonds going to the hydrogens. And so each of those are a sigma bond. And then it has this double bond here between the two different carbons. And so that is a sigma bond and a pi bond. And we'll talk about where that pi bond comes from in just a second. So that means that each of these carbons has to form 3 sigma bonds and 1 pi bond. And so, like I said earlier, the carbon atom will hybridize in such a way that it will form a number of hybrid orbitals equal to the number of sigma bonds that it needs. And so this means that the carbon is going to form 3 hybrid orbitals. And so let's take a look at what that looks like. Let's draw our orbital diagram just like we had before. So here's our 2s and our 2p orbitals. So this is what carbon would look like alone before it bonds. But now it's going to hybridize. When hybridization occurs, we'll always take an s orbital, always, 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 and then we'll take a number of p's that we need in order to form our 3 hybrid orbitals. And so we need 3 hybrid orbitals. And so this means that all we need to take is 1 of the s orbitals and 2 of the p's. So 1s and 2 p's in order to make 3 what we now call sp2 hybrid orbitals, because we only needed 2 of the p orbitals in order to make these. We now take 1, 2, 3 of the electrons are going to go into there. The 4th electron, keep in mind what we haven't used here. So what we have used is 1 of the s orbital, or the 1s orbital, and 2 of the p orbitals. We still have a p orbital that hasn't been used. That's where the 4th electron is going to go. And so now this carbon atom is able to make its 1, 2, 3 sigma bonds that it needs to, hydrogen, hydrogen, and 1 of the bonds going to the other carbon. Where do you think this pi bond is? It's going to result from this unhybridized p orbital. And that's where pi bonds live, so to speak, is in unhybridized p orbitals. And so if we sort of start to draw this, and this is where things get a little bit messy, but I'll try to draw this as best I can here. And so here we have our carbon double bonded to carbon. And we have our hydrogens hanging off that. And so each carbon is going to form 3 sp2 orbitals. So let's draw those in here. One of those sp2 orbitals will be coming out to this hydrogen. One will be coming out to this hydrogen. And one will be coming out to the carbon. And so there, and just to color code it here, so in the blue, those are our sp2 hybrid orbitals. And that is where our sigma bonds live. so that then the hydrogen can come in and just overlap with its s orbital, with its s electron, and form our sigma bond between the carbon and the hydrogens. And this other carbon is going to form its sigma bond as well, or it's going to form its three sp2 hybrid orbitals rather. And so we would have that overlap there. We still have the pi bond, however. And so remember that pi bond is going to live in the unhybridized p orbitals. And so if we draw that in too, and this is where things start to get really messy, but sorry, our unhybridized p orbitals. So here's our p orbitals that are still there in the carbon atoms. Those haven't been used. It's still just our p orbitals. But that now is where the pi bonds live. And so we have, again, sort of our color coding, our unhybridized p orbitals. Those are our pi bonds. Let's look at yet another example. Let's take a look at ethine. So carbon triple bonded. And so now if we, again, just look at this one carbon here, we can see that this one carbon is going to need one sigma bond between the carbon and the hydrogen. One of these bonds in the triple bond is a sigma bond. And so the carbon's going to need two sigma bonds, and it's also going to need then two pi bonds. So the same thing, we have our unhybridized orbitals with our 4 electrons there. But now we see that we only need 1, 2 hybrid orbitals. And so we're going to take the s orbital, and now we only need to take one of the p orbitals in order to make our 2 hybrid orbitals for the sigma bonds. And so since we only had to take one of the p orbitals, these are sp hybrid orbitals. 2 of the electrons will go there. We still have 2 unhybridized p orbitals that we haven't used. And that's where the 2 different pi bonds will live. Now, I'm not going to draw that one out because that starts to get fairly complicated. But it would look very similar to what I just drew out for ethene. And so these are hybrid orbitals in a nutshell. It gets even a little bit more complicated when we have expanded octets. And so remember expanded octets from Lewis structures. Something like, SF6 is a good example. So there's SF6. If we look at our sulfur, sulfur has 1, 2, 3, 4, 5, 6 different single bonds going to it. And so now sulfur would need to make 6, no idea why I wrote the letter G, 6 sigma bonds. Now if we take the S and we take our P's, that's going to get us to sp3. That gets us to 1, 2, 3, 4. We still need to take 2 more. So now we're going to steal 2 of the D's as well. Gets us to sp3 d2 for a hybrid orbital. So it starts to get kind of complicated there, but it's still the same basic idea that the orbitals will mix together and will hybridize in such a way that they will form an equal number of hybrid orbitals to what they need for sigma bonds. And so one of the ways to remember this, one of the ways to be able to recognize the hybridization of an atom is to simply count up how many sigma bonds it's going to need. And so let's take a peek. Let's look at some examples, because this is something that you'll need to be able to do, is to look at an atom and identify the hybridization of that atom within a compound. And so let's say we have carbon tetrachloride. Here's our Lewis structure for carbon tetrachloride. Very carcinogenic, very nasty type of compound. So there's our Lewis structure for it, though. And if we want to know the hybridization of carbon, the first thing we're going to do is count up how many sigma bonds does carbon have. Carbon has 1, 2, 3, 4 sigma bonds, and that's it. So 4 sigma bonds, which means that carbon is going to need 4 hybrid orbitals. And so it's going to, an s orbital will always be taken to form hybrid bonds, always, always, always. Now, even though we don't write it, picture a little 1 here, because that's 1. You can picture that as being the orbital that's going to help form one of our sigma bonds. And so now we still need 3 of the p's, though, to get us to our 4. And so that tells us that this carbon is going to be sp3 hybridized. If we look at, let's take a look maybe at acetone would be a good one. And so acetone, Lewis structure looks like this. And so again, we want to know the hybridization of carbon. And so we do this, we go through the same process. We count up how many sigma bonds are going to be on carbon. We get 1, 2, 3 sigma bonds. Because remember, the other bond here in our double bond is a pi bond. So we have 1, 2, 3 sigma bonds, which means we're going to need 3 hybrid orbitals. S will always be one of those taken. So now we're going to need to steal 2 of the p's. And so the carbon in acetone is going to be sp2 hybridized. And that's how you identify the hybridization. Count up how many sigma bonds you need. Let's actually look at one more. Let's see here. So if we have the compound phosphorus pentafluoride, our Lewis structure looks like this. And now I want to know the hybridization of phosphorus. So phosphorus needs to make 1, 2, 3, 4, 5 sigma bonds. So I need to make 5 hybrid orbitals. And so I'm always going to take an S. There are only 3 p's available to take. So sp3, that only gets me to 4 hybrid orbitals. So that tells me that I'm going to need to also take 1 d orbital. That gets me to my 5. So the phosphorus in this compound is sp3d hybridized. And there we have it. That is what hybridization is all about. This is probably one of the more obscure concepts that we're going to look at this semester. And so if you need to go back and rewatch this, go back and reread the textbook, do not feel bad about that. This will take you going through it a couple of times probably before it starts to sink in a little bit and make a little bit of sense. That does cover all of our material for Unit 3, however. And so that is it for this unit. You've got your test coming up on Friday of next week. And so study hard for that. And if you have questions, as always, you know where I am. Have a good day.